So in this video, we're going to talk about ionic equations. And an ionic equation is basically an equation which ions are explicitly shown. Okay, and so there's three different types. You have molecular ionic equations, complete ionic equations, and net ionic equations. All right, and what we're going to do, we're going to start off with molecular ionic equations, and from molecular ionic equations, we're going to derive and we're going to make the complete ionic equations. And then from there, we're going to take the complete ionic equations and make the net ionic equation. All right, and that's basically the end goal, because really we want the net ionic equation. Okay, and we'll just talk about the step-by-step process of how do we get to that point. Let's go ahead and start off with an example. So here's a chemical reaction. All right, it's just full of, this is ionic compounds bonding with one another, going through a chemical reaction. So this is, we know we have an ionic equation here. All right, so this example is a molecular ionic equation. Okay, so pretty much all the equations that you've probably seen in the past on the examples from the past videos, especially when we're dealing with aqueous ionic solutions, all of them I've shown you all have been molecular ionic equations. Okay, so how do we go from a molecular ionic equation to a complete ionic equation? Okay, and so in solution, just kind of give you some backdrop to this. So in solution, anytime you have a ionic compound dissolve into water, right? So here's my container of water, all right? And so for example, let's talk about KOH. And so if you were to pour KOH, all right, solid, right? If you had KOH solid and you pour it into the water, what you will see is that KOH, it's going to break up into its respective ions. So you're going to have potassium ions and hydroxide ions floating around. All right. And so the complete ionic equation basically illustrates this, and it shows that in solution, you don't really have potassium bonded with hydroxide. Really, they're separated out into their respective ions. Okay, and that's what we're going to write here. So I'm going to erase this very quickly. So anything that's in aqueous state, like this, or this, we're going to separate them out to its respective ions. So what I'm going to write is K plus aqueous plus OH negative aqueous. Now it's important that you state the charge, because remember, they're in its ion, it's in its ion state, so they have their charges. Okay, so you must make sure you include that. Plus we have HNO3, right? But it's aqueous, so we're going to break them up to its respective ion. So we have the hydrogen ion, which is aqueous, plus the nitrate polyatomic ion, which is also aqueous. All right, arrow. So we're going to this side. Now, this is not aqueous, it's in its liquid form. All right, and so if it's not aqueous, we never split them up. So if it's solid, liquid, or gas, we don't split up, because that's exactly how it truly exists in nature. That's how it exists within the experiment itself. So in this case, I'm just going to write H2O liquid. Leave that as is. All right, that's a cursive L, that's not an E. Anyways, and then we have potassium nitrate. You notice this is in its aqueous form, so we're going to break it up to its respective ions. NO3 aqueous. All right. Whoa, let me erase this real quick. Fix this. NO3 negative aqueous. All right, perfect. So now we have what we call the complete ionic equation. Okay. Now what we're going to do, we're going to go from the complete ionic equation to what we call the net ionic equation. Okay. Now to do that, what we need to first identify, what we call spectator ions. Now spectator ions are ions that exist on both sides of the equation unchanged. Okay, so you want to look at your complete ionic equation and look at, okay, what ions exist on both sides unchanged. Okay, and so hopefully you notice that in this scenario we have potassium ion that exists on both sides unchanged, and we have the nitrate ion that exists on both sides unchanged. These are our spectator ions. So your spectator ions, they contribute nothing to this chemical reaction because it never changed, right? It started out as a potassium ion, and at the end of the reaction, it still is a potassium ion. So it's like a spectator in a game, right? The fans, right? They really do nothing, right? So basically what we're going to do when we write the net ionic equations, we're going to eliminate or not include these spectator ions. We're going to include the non-spectators, I mean the real players of the show. All right, the net ionic equation basically illustrates which ions actually took place within the chemical reactions. All right, and the ions that are the substances that really took place in the chemical reactions. And when we notice that we have OH, H, so these two do not reappear or do not reappear in the product side. So we got this, right? And so we're only looking at substances that are not copied again on the other side of the reaction. And so we're going to rewrite this, and this is the net ionic equation where you have OH negative aqueous, the hydroxide ion, plus the hydrogen ion produces water. This is the actual chemical reaction, okay? And this is the reason why net ionic equations are so useful to us. It's because it pinpoints what part of what substances within the ionic compound was actually participating in the actual chemical reactions. It kind of takes out all the little the noise out, all right? And you get to see exactly what is taking place within the chemical reaction. So let's go ahead and look at another example. All right, so here's a chemical equation here where we have cadmium 2 chloride reacts with ammonium sulfide to produce a solid cadmium sulfide and an aqueous ammonium chloride. Okay, and so from here, what we're going to do from this molecular ionic equation, we're going to write the complete ionic equation. And remember, we'll just write the ions how it really exists. Remember, so we'll take all the aqueous and we'll break them up to its respective ions. All right, and then if it's a solid, liquid, gas, we just leave it as is. All right, so let's look at this first example. So we have cadmium 2 chloride is aqueous. All right, so we need to break them up to its respective ions. All right, and so we have cadmium here, and if you notice, it's bonded to chlorine, right? Chlorine's a -1 ion, but there's 2 of them, so that tells us that cadmium must be a +2 charge. So I'm gonna write Cd +2 aqueous. All right, chloride is typically by itself, so it's a negative, right? But how many do we have? We have 2 of them. So this is the way you write it. All right, it's different from a molecular chlorine where it's Cl2, that's neutral, but when it's chloride, it's always by itself, it's a -1, and if you have multiples of it, you need to show that by putting it as a coefficient. Okay, so aqueous plus, let's look at our next batch, ammonium sulfate. All right, we know that ammonium has a NH4 plus. How many ammoniums we have? We got 2 of them. All right, plus, oh, we need to write it's aqueous, plus sulfide. So sulfide, because ammonium is a +1, sulfide is only 1 of it, so we know sulfide is a -2 charge, and that's aqueous as well. Okay, yields, notice this is a solid, so we'll write that as is. Okay, plus, so here's our compound, it's aqueous, so we're going to break this up. So we notice that we have 2 ammoniums, so I'm going to write 2 NH4 plus aqueous. All right, plus there's still 2 chlorides, so I'm going to 2 Cl negative aqueous. All right, so this is our complete ionic equation. Now, to go from the complete ionic equation to the net ionic equation, we're going to have to identify our spectator ions. All right, so we need to figure out whom are our spectator ions. Remember, spectator ions are ions that go unchanged from the reactant to the product side. There's no difference on either side. All right, and so when we're looking at this, right, if you go look through this, hopefully you notice that, look, chlorine, chloride, two chlorides. So this is a spectator ion. Also, hopefully you notice your ammonium ion is also a spectator ion. Okay, it doesn't go through any changes throughout the chemical reaction. And so the real players of this chemical reaction is this cadmium ion, this sulfur ion, to create this cadmium 2 sulfide precipitate solid. Okay, and so when we rewrite this, we're going to have CD2 plus aqueous plus S2 negative aqueous to form CDS solid. Okay, so this is the net ionic equation for this chemical reaction. Now, we could use net ionic equations to apply for redox reactions as well. Same process. It looks just a little bit different, but I mean, not so much. Let's look at this example here, where we have a copper solid reacts with a silver nitrate solution to form a silver solid, and it will form a copper nitrate solution. All right, that's AQ. It is, I promise you. All right, so just like what we did last time, go from the molecular to the complete ionic equation. So anything that's aqueous, break it up to its respective ions. If it's not aqueous, leave as is. So copper solid, leave as is. Okay, plus this silver nitrate solution. All right, it's aqueous, so we're gonna break this up. So if you have Ag plus aqueous, and then you have 2 nitrate ions, aqueous, yields this 2 silver solid, will leave as is, and then we have this copper nitrate solution, so we're going to break this up. So we're going to have 2 copper, so this is a copper 2 salt nitrate. Since it's copper 2 nitrate, this is going to have a +2 charge, aqueous, plus the nitrate, this 2 aqueous as well. Okay, so this is our complete ionic equation. Now what you need to do is identify your spectator ions. Now remember, your spectator ions are basically ions or substances, species that goes unchanged throughout this chemical reaction. All right, and including charges. All right, if you notice the charge change, then it changed. All right, if it doesn't change at all, then it's a spectator ion. In this case, you'll notice that there's really only one spectator ion, and that's your nitrate. All right, the nitrate goes from it's 2 nitrate negative at the end, it's still 2 nitrate negative. All right, and so your net. So the real players is you have this copper that starts off with a 0 oxidation and it becomes a +2 oxidation. All right. And I just realized that I don't know why I include this 2 here. This 2 is not supposed to be here. I apologize for the confusion. Anyways, going back to what I was saying. So copper +2. Right, so it goes from a copper 0 oxidation to a copper +2 oxidation, and then you have this silver +1 oxidation that goes to a silver 0 oxidation. All right, and so when we rewrite this for our net ionic equation, you have Cu solid plus 2Ag plus aqueous yields 2Ag solid plus Cu2 plus aqueous. All right, and so this is the net ionic equation for this redox reaction.